Thanks, Dekai, and good afternoon, everyone. Thanks for coming to my talk. So this is work done primarily by Michel Galley, but he couldn't be here, so I'm giving this talk on his behalf. And this also joint work with Jianfeng Gao. So yes, so this is on large-scale expected BLEU training. And okay, so the main motivation of this work was work by actually Colin Cherry, who like last year had a very interesting paper at NACL showing really huge gain of quality on a phrase-based system, where he was showing that using sparse features and optimizing those sparse features directly on the tuning set, he could gain very impressive gains. So, so what we did in this work is actually we extended his work and try to, with a maximum expected BLEU training objective function, to directly optimize a much larger set of features, and this time not on a tuning set, but directly on the training data. And so what we achieved in this work is we're able to scale to millions of features, and also to full-scale training sets. In our experiments, 100 million training works, and also, it's a relatively fast approach, so which requires decoding the training data only once. And we also achieve significant improvement with 1.6 BLEU point on a WMT French-English setting, and this is a single reference. And okay, so a little bit of background. So of course, like most of you are familiar, this is a phrase-based decoding framework, and where the target string is decoded left to right. And so I would like also to stress that the importance of this kind of work on lexicalized Reordering models. And so this is really a key component, because as opposed to other kinds of decoder, like higher, there's no intrinsic notion of ordering in those models. So all the ordering capacity is delegated to this component, which are lexicalized Reordering models. So, okay. So to explain how these models typically work, I'll go through a running example. So again, in a typical phrase-based decoder, you decode the target sentence left to right, and you have, let's say, you hypothesize the first phrase development, and then the second phrase and progress. And really, the task of a Reordering model is to tell you what's the likelihood of this given phrase and progress being in a given orientation with respect to what comes previously. And here, like, you want to know what's the likelihood of a monotone orientation. And here, the next phrase of region. So here, what you did is like went back in the source string, and you grab words that were not contiguous with what was grabbed previously. And then again, you want to estimate what's the likelihood of this orientation with respect to what was previously, and so on. And okay, so that's kind of the first kind of models were proposed for lexicalized Reordering models. And then this work was extended by noticing that, well, if you have this kind of simple local model, often it doesn't explain the data very well, and you end up having the discontinuous orientation being hypothesized a lot of times. And also, like with this kind of model, you don't have really consistency across derivations. So then it was a hierarchical Reordering model was proposed, which maintains the shift-reduce parser, which is tracking what contiguously covered spans. And this orientation assignment, then they are more consistent across derivations. And so, for example, here, when you're hypothesizing the new phrase of a region, this model would identify that it's in a swap orientation with respect to what comes previously, and so on, and then monotone orientation when you're hypothesizing the last phrase of a sentence. Okay, so now a little bit of background on how this kind of model is typically estimated. So, like, let's say this phrase, how would you score this given block for a given orientation monotone? Okay, so the earlier work was just doing simple counting, and that's very easy, but so that scaled easily. So you basically, for a given phrase, you count the number of times you see that given phrase in the training data in a given orientation. And that yields like a very large number of parameters, which is nice because you can really fit your data, but also in a certain way, it also massively overfit because most of these translation units are very sparse. There are a lot of singletons, and actually in a typical phrase table, actually in a, you would have like maybe 90% of singletons. So the estimation that you get for these models is really poor. And another downside is like those models are, the objective function is likelihood, so there's a problem because this might not actually correlate at all with the final task-oriented objective function, which is typically BLEU, or some other assessment of translation quality through a metric. Okay, so the next step was to go with some kind of log linear approach with maxent Reordering models where rather than having this huge set of parameters that are really specific to any given phrase, here we kind of try to come up with features that are much more general, so like word-based features, let's say features that fires for like the first or last word of a given phrase. So with this kind of approach, you can still train on full-scale training set on the full byte text, but the nice thing here is like this linear model, I mean, you still come up with millions of parameters, but the estimates are much better because you benefit both from these rare features that are like the occurrence of a given phrase, but also the more generalizable features that are like single words. So that's kind of nice. But the disadvantage of this is like you're still training towards likelihood, and again, no BLEU objective in this work. So okay, so now I'm gonna refer back to the work I mentioned initially, the work of Colin Cherry, where he showed that, well, if you have this parameter vector like theta, well, if you tune this theta directly with, let's say, Mara towards optimizing BLEU on a given depth set, then you're actually much better off, and he was showing like a very significant improvement. So that's really nice because then the training data, the actual training data that you use to tune this parameter theta is actually the actual representative of your translation output, and it's an objective function that is BLEU sensitive, and it works much better than a maxent model. Okay, so that's kind of the situation we're at. Like sparse features and Mara work better than simple relative frequencies, and one reason hypothesize it's like there is a BLEU objective in the loop. But on the other side, the number of parameters kind of really dramatically decreased, where with relative frequencies, you would have like 500,000 parameters, and then Colin Cherry went down to 3,600. And also in the amount of training data, you're actually no longer training on the actual training data, but more on the depth set. So that's perhaps a problem because when you're tuning on depth set, you might capture like stylistic phenomena or perhaps things that are kind of really particular about the depth set, and maybe you really want to train on the full scale training data, which is what we do with a maximum expected objective. So we go up to 3 million of parameters and tune to full training sets. Okay, so to give a bit of an understanding of how an expected BLEU objective works, I'll start by explaining how of a more familiar setting of doing likelihood optimization. So you have some kind of probability model like here, where you want to maximize the likelihood or conditional log likelihood of say, references with, so you want to optimize the set of parameters to maximum likelihood of it. And okay, but typically the reference is not part of your gen set. So what people do, well, there are different ways of going around about this. So maybe you would have some restricted view of a gen set, let's say an n-best list or maybe a lattice, and you say, okay, the k top or maybe one top hypothesis in that gen set with respect to, say, BLEU is the positive instance, and all other remaining ones are the negative instances. So you make kind of this arbitrary choice between what is positive and negative. And the expected BLEU objective, as opposed to that, does something different. So it's, well, again, it looks at the gen set, and it's sensitive to the human translation, and basically it will weight the goodness of a given training instance with respect to a measure, let's say BLEU here, and it gives, so in the sense that it upweights things that have highest BLEU scores and downweights the one that have lowest BLEU score. So, okay, so now to explain how this actually works, doing expected BLEU training, so I'll provide a small example to explain how this works. So let's say you have this input Chinese sentence, the human translation is development and progress of a region, and let's say the gen set here is a simple n-best list, so I keep the example relatively simple, and say here's the BLEU score you get for each element of this n-best list. So here this sentence level BLEU score, so this is smoothed, and let's say you have a given model for which you can build a probability distribution, let's say with softmax, and here you're in the training stage where you can see from this mark in blue here that basically the model prefers those translation that has kind of lower BLEU score. So the probability mass is still on those elements of the n-best list that have low BLEU score. So the step of expected BLEU training is basically relies on first computing the expected BLEU of the n-best list. So this basically does the cross product, dot product between expected BLEU, sentence level BLEU and the probability under that model, and it gives you for this n-best list an expected BLEU of 0.5. And basically now you have an error term here that is the delta between the actual BLEU score of a given hypothesis and the expected BLEU score. So for example, in the first line, the actual BLEU score is 0.8, and the expected BLEU score is 0.5, so you have a delta of 0.3. So that's the error term, and basically what you're going to do here is basically you will update the parameter as to give more weights to those elements of the n-best list that have positive delta and give negative weights to those that have negative delta. And then, okay, so this goes next to online. This is more like natural to train in, say, a kind of online learning algorithm where then the update, after the update, again, you can turn this, according to the model, you can turn this into a probability distribution, and after this update, you would have the likelihood of those sentences that has high BLEU score, they have high probability according to the model, and the ones that are that have a negative delta, they have a lower likelihood. So for example, here the third element of the n-best list progress of a region with this delta of minus 0.2 yield to a decrease of probability, and which is exactly what you want to achieve. And then by this step, you actually increase the expected BLEU score of this given n-best list. So that's how it works on a simple example. And now the question here is like, well, how do you want to scale this to a full training set? So we can come up with some kind of trade-off here where like doing this kind of training, expected BLEU training on the full training data is expensive. So we come up with this approach where we train, we optimize the sparse features with one pass, but in a way that requires only one pass of training data, and for the dense feature, we go iteratively generating new features. So the first pass, what we do is like we decode the entire training data with a baseline SMT system that has only dense features. So we generate n-best list for, in our setting, is 2 million sentence pairs, and so that's generated from the baseline system, and we use n-best list, but we could conceivably also do this with lattices. And then on those n-best lists, we optimize for expected BLEU using a stochastic gradient descent with this expected BLEU objective, and that refers back to the previous slide that gives you this motivation, and also the details of algorithm of how to apply expected BLEU is in more details in the paper. And then once we're done training with expected BLEU with millions of features, we turn, so then the weights are fixed, and this is those features for the lexicalized Reordering model are turn into dense features because those weights are fixed. And those weights then are added to the baseline system on which we, again, do MERT optimization, but this time with a handful more features. And that's how the entire pipeline of training in our setting. Okay, so now some words about the feature set what we used. So the core set of features is essentially based on Colin Cherry's feature set. So it's basically a set of indicator features, unigram and indicator features that are derived from the given phrase. So let's say you have this phrase of a region, and Colin Cherry uses first and last words of a phrase, both on the source and of the target. And it does this also for the hierarchical block preceding that phrase. So again, 4 features that are derived from these hierarchical blocks. And so that gives you this kind of feature functions like discontinuous source or target of a word off. But then that would yield like millions of features if we do that. So what it does to restrict the number of features, he does this kind of feature extraction only for the 80 most common, most frequent words, both for source and target. And also he uses Brown clusters to learn features that are a bit more general. So he comes up with, at the end in his experiments, like 3,600 features. So, I mean, now we scale it up, and so beyond those frequent words and both, so okay, here we make a distinction between the local features, the one that only depends on the current phrase, and also more the global features that also use the previous block, and that yields like 9.4, about almost 10,000 features. Now, as said, he used only frequent words. We do also that with all the words, so that yields up to 1 million feature types. And also we use as features source and target phrases and the combination of source target. And that goes up to 3 million features in our experiment. Okay, so here are the results with these different feature sets. So in our experimental setup, it's a WMT from the evaluation campaign of 2012. The amount of data is a bit more than 100 million training words, and we use 6 different test sets, and it's going to report like aggregate results on these 6 test sets. And a baseline system is basically a decoder that is in spirit similar to the Moses decoder. We use a 4-gram language model, and we have 4 orientation, monotone swap, and we make the distinction between left and right discontinuous. And the evaluation is uncased BLEU, and we use single reference. Okay, so now these are the main results of this work. So, and here you see the indication of number of features that we have. With the HRM, you get this performance, and then adding the Colin features in our training setting, not his training setting. So in the setting where we train on the full training data, so we get a 1 BLEU point improvement and 1.2 with also including non-local features. You use all the words of the vocabulary, you go up to 1.4, and with all the phrases, plus 1.6. And again, this is single reference, so it's harder to get search gain than, say, typical niche setting where we have 4 references. Okay, and now see how this scales by increasing the amount of training data. So again, if you have a dev set size kind of setting like in Colin Cherry where you use like 2,000 sentences for tuning, for training, then you get this performance at the bottom. But on the test set scaling to 272,000 sentences per you get a significant gain on top of Colin Cherry's setup. And it's also to make a distinction here between likelihood training and more between the expected BLEU training and the more standard likelihood training. So with likelihood training, you only get 0.3 BLEU point improvement compared to the baseline, but if you do expected BLEU objective, you have 2 plus 2 BLEU points. Just to mention, this is a test WMT 2011 test set. So it's not directly comparable to the other slides. And comparison to Pro. So Colin Cherry uses Myra. We're more confident with our Pro experiment. So we have a pretty competitive Pro implementation, and this is how this compares Pro and expected training, and and we get 1.2 BLEU point compared to Pro, which is really designed to tune on a dev set size kind of setting. Okay, and it's relatively fast. So okay, again, this requires you to decode the entire training data, but this is done only once. And once this is done, and well, decoding also, we can easily parallelize this. But after that, we do the training, and for example, here for training with 3 million features, we need just about 2 hours with 140,000 sentence pairs. Okay, and a bit of related work. So there has been related work on this large-scale discriminative training, but with also including an expected BLEU objective, but here we really go, it's one of the first work where really we go towards millions of features, and really the work that is most comparable to our work in terms of number of features of the max violation perceptron. And I'll note a few things, differences here between their work and our work. So in our expected BLEU objective, we give partial credit, whereas in max violation, you have only like a binary categorization of instances, and we are able to train on the full training data, whereas in max violation, you have to restrict yourself to what can be force decoded, and their updates is only based on one best and references, but we use the full training data. So in conclusion, we did a large-scale expected BLEU training for reordering models. And so the update is very easy. The training setup is very easy to implement. It's scalable, and we can train up to, millions of features on full-scale training sets. 1.6 BLEU point improvement on a single reference setting, and it requires only one pass on the training data. So that concludes my talk, and thank you very much.
Anyone have a quick question with a quick answer?
So hi, I'm Jan Wipka from Aachen University, and when you added all your different types of features, you started with the more general ones, right? And then you increased the granularity at each step. What I'm wondering is if that is actually necessary. If you, at the point when you add this all phrases features, you still need all the ones before to get the same performance.
Yeah. So okay. Yeah, that's kind of shows here with its results. There's it's not as important as going to using those most general features. But so here, for example, you go only, 0.6, which in a one reference setting is still pretty good. Yes, so there's benefit, but I guess a slight diminishing return, I think.
So have you actually tried using only the all phrases features and not training the all words, frequent words, and the other ones?
Yes, we tried, and yes. So I don't remember exactly the results, but the results were pretty significant. It was not as good as like removing those more general features. So there was a performance gap. So you need those more general features to get good performance.
Okay, yeah. Thanks.
Yes? Okay. Sorry for taking long.